Greetings and welcome to Artifact Electronics channel. What we're going to have a look at today is an HP Agilent 6612C DC power supply that is fully programmable and is capable of delivering 20 volts at up to 2 amps. I bought this through eBay and it was sold as defective for parts because the seller claimed that the supply even powered on, which is what you're seeing, but could not regulate the output voltage. So let's have a look if that's really true. So we should program this device now and see what happens when we program a voltage and a current into it. I noticed that the vacuum fluorescent display is flickering pretty good in the video. It's not nearly half that bad in real life. I mean, I can barely discern any flicker when I look at it directly, but the camera is sure making a big deal out of it. Anyway, when you power this unit up, the voltage and the current limits are reset to 0. So what I'm going to do is set those up. Also notice that the disabled annunciator light is on, which means that the output accessible through this button here is currently turned off. So to set the voltage, you go to the voltage button, enter number, let's do 5 volts. So it's now programmed to deliver 5 volts when the output is enabled. And let's choose 500 milliamps for the current. So nothing's changed on the display right now because it's monitoring what's coming out. And for all intents and purposes, the output's floating right now. So that's what it sees. But if we enable the output now, it's telling us that it's outputting negative 1.540 volts at 0.7 milliamps. Kind of a strange number. Let's double check that. The output gets turned off. We will bring a meter in DC volt setting. And now turn the output on. Well, looks like it is measuring whatever is appearing at the output correctly because this meter agrees with the voltage. It says that it's outputting no current at all, which also seems likely. So another thing to note is that the unregulated annunciator light is on, and that's basically telling us that the device is saying, I'm trying, but I cannot give you what you've programmed into me. So there's the problem. Could be one of many things, but let's take the device apart and have a look at the service manual, which is still available from the Agilent website. I went ahead and downloaded a copy of the service manual from the Agilent website. Turns out that this document is dated September 2000, which makes the power supply a bit older than I originally thought, and it's basically 17 years old. But unfortunately the schematic is of the newer kind in that there's a lot of textual information in there. There's a lot of information about remote programming, but it's a bit thin on schematics. It has the dreaded flowchart that look nice from a distance. but looking at a part of it or looking at the end part of it, one thing that's very common, as you can see, the final blocks in the block diagram basically say replace, 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 and so on, which I understand that if you have a board with a lot of custom circuits on it, that you may not want to reveal their pinouts, or it may even be moot to reveal the pinouts because you can probably not find the replacements for it anyway, or HP probably won't sell you individual replacements. So the logic here is probably let's just do a board swap repair, and that's the only way you're going to get this thing fixed. The closest we got to an actual schematic is a power supply schematic that I would judge to be rather sparse. It shows the power supply, but it's more of a block diagram than a schematic, I would say. There's no component values given for the diodes, the regulators. They have designators, PC board designators on the regulators, and I mean, at least they do tell you what the voltages are. But that's about it. I think the most useful part here is that we can see there are 6 fuses shown. And those are the fuses that for the voltages coming out of the secondary of the main transformer. And that would probably be a really good place to start testing. Now, another useful piece I found was a diagram of the fuse locations on the main board. And looking at this diagram, we find the locations of the 6 fuses that were shown on the power supply schematic. 1, 2, 3, 4, 5, and 6. However, looking at this closely, there is another fuse in the middle, F309, and I searched through the manual for F309, and there was a fleeting reference to it, and if you read that paragraph, it actually told you that F309 is the output fuse of the main voltage output on the device. So it'd probably make good sense to test the 6 fuses in the power supply, essentially just beep them out, and also have a look at F309, which, if the manual is telling the truth, is sitting directly on the output. So if there's anything wrong with that, that would probably explain the behavior of what we were seeing. The question still remains of why would that fuse blow, because it is listed as a 4 amp fuse, and the meter, the DC source itself is only capable of delivering 2 amps. But let's go in and check the fuses and revisit that if it becomes necessary. I went ahead and removed the case. It's basically held in place by 2 screws in the back and another 2 screws underneath. One of the screws was hidden underneath one of the plastic feet, one of these guys. So I saw one of the screws, removed it, and started pulling on the case. Of course it wouldn't budge, till finally I saw that the 4th screw was hidden by one of those plastic feet, and the screw was conveniently covered with a sticker. This wasn't a warranty sticker, but basically said if the sticker's broken, this unit is out of calibration. And it was still intact. So using the fuse layout that we looked at before, We can now go ahead and locate all of the fuses. This is going to be really difficult to see because even when zooming in, it doesn't look good. So I'll show you the general location of them. There are two through-hole fuses here and here. There is a surface mount fuse right here. There's another two surface mount fuses hidden behind this connector. And the sixth power supply fuse is hidden between these two capacitors here, and is also surface mount. Now the final fuse that is set to be the output fuse is somewhere else on the board. Looking at the diagram, it's about here, so we'd have to remove the digital board. I've already gone ahead and removed the screws that were holding the connectors, the GPIB and the serial connector in place, and that's what's holding the digital board itself. We can now slide this out. And gently flip it and lay it down. Quick rundown of the digital board is there's a TMS 30C32 DSP. This is Xilinx part, another TI part, something that looks like EPROMs, and glue logic and whatever else. We can also see a nice factory mod right here where two resistors have been soldered across a chip. It's clean enough to be a factory mod, but nonetheless it's still a blue wire, or a bodge job as it's commonly called. So if we zoom out again, and this time going over here, right next to this 0 ohm resistor, we can see the output fuse, which is designated by F309. I'm going to go in now and do a continuity test on all of the fuses. Since things are so hard to see, I will quickly do this off camera and come back with the results. And the winner is, I measured the 6 power supply fuses. Some of them are really hard to get to, and I had to make sure that I wasn't getting false readings because the probes weren't touching. But finally the 6 fuses in the power supply all beeped out and were good. I then measured the output fuse over here, and lo and behold, it was open. I tried it 3 times, but yes, it's open. It's a through-hole part, so in order to remove it, I can probably remove this from the top by heating the solder pads and lifting it out with tweezers. That's still not going to solve the problem of how to replace it, because obviously proper replacement would dictate me removing this board and doing a clean job. But if we look at this a little bit more closely, which I have done already, is everything's so tightly packed that in order to get out the main board, I would have to unplug all of the leads on the transformer, remove the transformer, remove the main heatsink for the regulators, and that poses a bit of a problem too, because certain screws are hidden behind heatsinks here, and getting to that is going to require me removing this regulator to get to the screw behind it. There are a bunch of issues like that. So what I'm going to attempt to do is, the desoldering part is going to work. Shouldn't be a problem. Just heating it from the top and lifting it out. But putting back the new part and getting a secure connection and not shorting it is going to require some careful thought. But first things first, let's remove the offending fuse. I was able to remove the fuse relatively cleanly with no lifted pads or anything like that. Clean things up around it. And the fuse over here is clearly labeled as a 4-amp fuse, and yes, it's still open, even out of circuit, as if that would have made a difference. Now, here's my replacement fuse. Let's see if I can. You can't really see what it reads on it, but it is a replacement 4-amp fuse. The problem still persists of, I'm going to insert this fuse from the top, solder it from the top, assume that, the vias, the through holes are still good. I only have to be very careful with the leads themselves so they don't touch the case or short something. And the way I'm going to do that is, first of all, measure, using one of these guys, measure the wire spacing on the fuse I removed, which is 0.45. Then use the new fuse, the new fuse is bigger and doesn't even fit into the 0.45 slot. So and it doesn't fit in the 0.5 slot either. So I'm just going to bend it by hand. And the way I'm going to make sure that we don't short anything is I will use the blown fuse. I will clip the leads to the same length as the leads are on the blown fuse, and that's going to make it. I'm going to be pretty sure that is not going to touch the bottom. Another test I will do very quickly is get a resistor and use it as a depth gauge. And that's going to tell me how much room there is under the hole. So take this, stick it in the hole, and mark it. So now, oh, that's just great. I can't see the mark. There it is. It's very faintly right next to the R if you look closely. So that actually tells us there's plenty of room in there, and clipping these leads to match the blown fuse should be enough of a safety to guarantee that we're not shorting it to anywhere. So using the wire clippers off camera, and here is the result. And I will attempt to insert that in the holes now. This is taking too long. Let me take this off camera and we'll be back. I managed to insert the new part into the hole and soldered it into place from above. So let me clean that up a little bit, put everything together, and see if it made any difference in the operation. It's very hard to see, but the new part, I've left it slightly elevated off the board. And the reason for that is that if I put everything together turn on the output and the thing blows again, it's going to make it a little bit easier for me to remove this time because I can get an easier grip on it with pliers or tweezers. So let's hope for the best, put it together, and see what happens next. I know I said I was going to put the case back on before testing it, but on second thought that seemed like a really stupid idea because we don't know if the problem is fixed or if the minute we enable the output at some voltage, it's just going to blow the fuse again. So I left it open. I put the digital board back in its place and fastened it from the back. So now it's time to test and see if we're getting an output. Well, if we're getting an output and if the fuse is going to hold. So let's select voltage and we enter, pick a number, 3.3 volts, and the current, we'll set that at 500 mils. If we hit the right button. So let's try this again. Well, yes, it's not going to output 53 amps. So let's do this again. Current, enter number 0.5. So it's set to 500 mils at 3.3 volts. And now we will enable the output. And in my excitement, I pull off the ground lead. And look at that. It's showing 3.302 volts with no current consumption, which it's not consuming or it's not sourcing any current because there's no load on it to speak of. But it looks like our voltage regulation is right on. Now, what this proves is that it can regulate voltage without a load, but in order to test this more properly, we have to give it a real load. And let me drag out a piece of equipment or something that is going to consume some real current and see if we've really fixed this thing. So look what the cat dragged in. This is actually one of my future projects. It's an 8-inch Sony Trinitron TV. It has a blown internal power supply. The AC switcher in it is bad, but I discovered that you could still power it off external 12 volts DC, probably using around 18 watts through that input. So this should provide a good test to see if the DC source can handle it. Some of you may be yelling at the screen right now and saying, why, you have the black and red inverted. It's an astute observation, but the reason for that is that my adapter plug, the red is the center pin. I mean, it uses just a standard power pin, and for this TV the center pin is supposed to be negative. So that's why the red plug is on the negative input. So let's set up the power supply now. The voltage, it wants 12 volts. So we go and give it 12 volts. And I think, yeah, it's about 18 watts. So I'm just going to give it full current, full current capability of this guy, which is 2 amps. So this is the big test. I will now turn the output on and see what happens. Oh. And there you go. It's in video mode. It powered up. I don't know if you can hear it, but the fan just spooled up in the power supply. So it knows that it's supplying a real current right now. The 12 volts is right on. I think we've already proved that the voltage measurement in the device is pretty accurate because we looked at it with a voltmeter last time. So it's holding steady at about 1.25 amps. Now I know that if we switch it from video mode to TV mode, it's going to use more current, and let's do that right now. And yes, current consumption jumps to just over 1.5 amps. The voltage is still steady. I don't have a digital tuner handy, so we're just going to have to look at noise here, but it's showing beautiful noise. The fan has ratcheted up in speed a little bit more because, it's dancing around, but on average it's probably, it just hit 1.6, so it's peaking out at about 1.6 amps. Let's see if raising the volume is going to make it consume more. A little bit more, a few hundred more milliamps, but the good news is it looks like it's fixed. I could use some other device. I'll probably test it with some other devices down the line, but I think this test pretty much proves that it is outputting the proper voltage, it is regulating it correctly, and it's able to power the TV. There are a number of tests and calibrations that would probably need to be performed, even though I haven't replaced any components per se. I've only replaced a fuse. But maybe in a future episode we'll actually go through the calibration steps on this guy. But for now, I think everything is fixed. Now I will finally put the case back on and we'll have some brief closing words. We finally made it to the end. It does need to be calibrated, but as I said, that is something I will do in the future. Again, don't let the flicker bother you too much on the display. It really doesn't. It's not flickering when you look at it with the brain scan rate, or at least my brain scan rate. The only mystery, of course, is how could a device that can supply 2 amps max blow its own 4 amp fuse? The only way it could do that would be if there was some major damage in the voltage regulation circuit. And since replacing the fuse, we see that it works just fine. So I don't think that this was caused internally, but rather by something hooked up to it externally that forced a current of more than 4 amps into the device and thus blew the output fuse, because the output fuse sits directly on the positive terminal. So I'll call that mystery solved there, and we have a working power supply. Well, I hope you enjoyed it. I'm sure you can't wait to see what the deal is with the TV we used. The best way to see that is to subscribe, because I will probably start working on that in a few days and see if I can get the internal power supply fixed on it and explain why I would even bother working with an analog TV. See you at the next episode.